All right, welcome to the first video for Chapter 5. So Chapter 5 is about bootstrapping, one of our prime techniques we're going to use for the rest of the course. That'll also serve as an introduction to confidence intervals. All right, so just a bit of a reminder of where we were to help understand where we're going here. In Chapter 4, we focused on calculating or approximating sampling distributions of a statistic T when the relevant population was known. Either the data set was the entire population or the population from which we pulled data was from a known distribution, okay? But in either case, knowledge of the population was there. Right, by the way, pause, copy, play. All right, well, it's far more common to have this second scenario. So what if all we have is a sample of data from a larger population whose distribution we don't know about, but we'd like to? Can we estimate the sampling distribution of the desired test statistic or the desired statistic? Let's say the standard error. All right, and that's sort of what brings us to finally the definition of statistics. Statistics is when all we have is data and a test statistic or statistic estimated from the data, we estimate the sampling distribution of that statistic. That's what doing statistics is, operating without knowledge of the population and trying to figure something out. Okay? Now, one way we can estimate the sampling distribution is via bootstrapping. Okay? So the idea with bootstrapping is to treat the sample that we have as the entire population, as though it were the entire population, and repeatedly resample from that original sample to create a sampling distribution. Okay? And that sounds like it could cause problems, and it can, and we'll investigate those. But also, it might be helpful to remember that the sampling distribution is if we have a desired test statistic, let's say the mean of a sample, if we resample 10 to the 4th times and each time calculate the mean, the sampling distribution is the distribution of all of those 10 to the 4th means, right? That was the sampling distribution. Okay, so let's look at bootstrapping in a bit more detail here. All right, so why don't you pause, copy this down, and then we'll start up. So we've looked at this file, North Carolina Births 2004, NC Births 2004, and it contains information about 1,009 births in the state of North Carolina in the year 2004. And it contains a bunch of information, the gender of the baby, whether the mother was drinking alcohol or not, smoking or not, using tobacco or not, how long the baby, how long the term of the baby was it carried to 40 weeks? Was it carried to 38 weeks? All that information, as well as the birth weight of the baby in grams. Okay. So this file, though, doesn't contain data on all the births in North Carolina in 2004. It's just a sample of 1,009. Okay. So the mean birth weight of this sample of 1,009 births is 3,448.26 grams. And the question is, how well does this estimate mu, which is the mean birth weight of the population of all births in North Carolina in 2004? Okay. All right. Well, here's how we're going to use bootstrapping to do this. So in bootstrapping, we start with a single sample of size lowercase n from a population. So in our case, we have 1,009 birth weights. From the single sample, I'm going to draw a sample of size n, 1,009, with replacement from that initial sample. So I got my 1,009 birth weights. I'm going to grab one birth weight, record it, put it back, grab another birth weight, record it, put it back, and do this 1,009 times. I might grab the same birth weight more than once. Okay, so resampling with replacement. So I do that 1,009 times, and that is my first resample of the data. Okay, when I have this first resample, I'm going to compute my desired statistic, let's say the mean birth weight, and record it. Okay, repeat that step at least 10 to the 4th times. So I'm going to have at least 10 to the 4th mean birth weights of resamples. And from those 10 to the 4th, I can construct a sampling distribution of this desired statistic. We call this distribution the bootstrap distribution of the statistic, okay? And then we can inspect that distribution to see where its center is and what its spread and shape look like in order to get the senses of what the mean and the standard error is, right? But there's going to be problems. All right, the last panel for this video. Okay, and we're going to do a little bit of R at the end here. So if I'm resampling n objects from a pile of n with replacements, then there are n to the n possible resamplings. I have n choices for my first item, record it, put it back. I have n choices for my second item, record it, put it back, n times. So that's where n to the n resamplings come from. And that's if order matters. First recorded, second recorded. Now, order doesn't matter though, right? It doesn't matter what the order of the birth weights I see is. I just want to look at all the birth weights. So it turns out there's only 2n minus 1 choose n distinct resamplings if order doesn't matter. And that's what you folks are going to figure out in exercise 5.5. So 2n minus 1 choose n is far less than n to the n, but it's still a large number if n is to 1009, for example. So we could try and use all of those resamples, but that could choke our computer just in terms of the time it would take. And we'd have to track each of the resamples we've done so we don't do any of them twice. So we'd have to store all the information about what resamples we've already computed, okay? All right, last definition here. The standard deviation of the bootstrap distribution of a statistic is called the bootstrap standard error, okay? Now, I'm going to switch over to NC births file on R, and I've got a value that I need to fill in here just to sort of illustrate how we calculate that bootstrap standard error, okay? But let's switch over. Again, the audio will get kind of bad probably. So first off, make sure you have clicked the resample button so R knows what files we're talking about. And we can view on line 7, this is a chapter 5 file in Canvas. On line 7, we can view the file we're looking at. And as you see, it's got all kinds of information: the mother's age, whether the mother used tobacco, whether the mother used alcohol, the gender of the baby, the weight of the baby, the gestation period of the baby, and whether the mother was a smoker or not. Okay, so all that information. All we are concerned about was this weight column. So the first thing we're going to do is line 9 here. We're going to define the vector of our data just to be the weight. So NC weight is going to be from the file NC births 2004 $sign, just copy over the weight column. Okay, so I'm just looking at the weights. Now, how many weights are there? Well, I could do the length of NC weights, and it looks like it's 1009, as I mentioned. And what I'm going to do is my test statistic is going to be the mean weight. So I'm going to look at my observed test statistics. So the original sample of 1009, define observed to be the mean of that. And if we spit it out, I get 3,448.26. Okay. Now, in line 16, I'm going to define capital N to be 10 to the 4th. And in line 17, I'm defining a vector, my.boot, to have length 10 to the 4th. And that's where I'm going to fill in my test statistics for each of these resamples. All right, so then lines 18 through 22 are where it's all at. So what I'm doing here, I'm going to do this for 1 through capital N, so 10 to the 4th times. I'm going to take my vector and see weights, and I'm going to sample 1009 values from that vector where replacement equals true. That means replacement is allowed. So that's going to be one resample, and I'll define it to be X. And then in line 21, I'm going to take the mean of X and record that in my vector, my boot, in the ith position. Okay, so let me run those lines. So there's line 16, line 17, and then running the loop. And there it goes. And so it's done that 10 to the 4th times. Now here's a histogram. There it is. And it looks kind of normal-ish. I'm going to put in a blue line where the mean of the original sample is. The mean of my boot is going to be 3448.121. I'm going to record that, 3448.121. And then I'm also going to ask it to calculate the standard deviation of the sampling distribution. And I get 15.42. Okay, so I've now recorded those numbers. So how did the R calculate that bootstrap standard error? Well, it did 1 over 10 to the 4th minus 1, did the sum of the mean of each resample minus the mean of all the resamples, square rooted it, and came up with 15.42 was the sort of the spread on this distribution. Okay, so we'll talk more about this in the next video.